talking about 9.2 orthogonal complements and direct sums. Can somebody tell me what an orthogonal, what is this stuff? What's an orthogonal complement? You have your vector space. Your vector space is Rn. You have S, a subspace, right? And then we have this thing called the orthogonal complement, right? What's the orthogonal complement? All vectors that are orthogonal. So, yeah, so how do I describe it? It's going to be all vectors in Rn so that what? X is perpendicular to any vector for all vectors in that subspace. Right? It's a collection of everybody who's perpendicular to everybody in your subspace. Okay, and then where we ended up last time was this thing called the fundamental subspaces theorem. Fundamental subspaces. And the name of this theorem confused me at the beginning. Because I didn't think there was anything particularly fundamental about it. But it's actually fundamental subspaces. It's not a fundamental subspaces theorem. It's a theorem about fundamental subspaces. Okay, so it's like this. It's not like this. I think one professor at Pitzer collects these sorts of things to show that English is non-associative. Right? She has some big list of things, some of which are humorous, but I don't know any of them. Okay, fundamental subspaces theorem says that if you have some matrix, then the null space of A is actually the. Well, can anyone tell me what is that? It's a little bit tricky to state. Yeah, Emma.
The orthogonal complement of the range of the transpose.
Right, the orthogonal complement. If you take the range of the transpose and then take the orthogonal complement of that, that's the same thing as the null space. Okay. And and we commented that if you put in this is equivalent to saying that the orthogonal complement of the range is the same thing as the null space of the transpose. Yeah, Mia.
So, I'm sorry, that orthogonal complement is all vectors perpendicular to the subspace?
Yeah, perpendicular to everybody in the subspace.
Okay.
Yeah. And probably I didn't make this clear enough, right? When we talk about R of A, this is the range of A, right? The range of A, and so that's all, right? All AX where X is in Rn. Right? It's all outputs of T sub A. It's really the range of T sub A. Yeah.
Is it the columns of it?
Yeah. So what does this mean, right? This is this is going to be a linear combination of the columns, right?
So
it's the column space, right? So this is the same thing as the column space of A. Everyone all right? Any questions on notation at least? Okay. Okay. So let's go on from let's go on from there. So now that we have the fundamental subspaces theorem, we then can use that to get some facts about orthogonal complements. Okay, so here's the theorem. Fact 1, if S is a subspace of Rn, then the dimension of S plus the dimension of S perp equals n. Okay. So, right, if you have a one-dimensional subspace in Rn, then you know that the orthogonal complement is going to be n minus one dimensional. Right? That they add the dimensions add up to 1. Okay. Number 2, if x1 through xr is a basis of S, and xr plus 1 xn is a basis of S perp. So if these things are so, then their combination, the union of these two sets, is a basis of Rn. I think I'll let you try. Try to prove. Try number 1. See if you can get anything about number 1. Right? Think. What kind of theorem? What kind of theorem does this remind you of? There's something that should. There's a tool that should sort of jump out at you. Take 2 minutes and just see if you can make any progress on this problem. You have a subspace. Why should it be that the dimension of the space plus the dimension of the perp is n? Okay. Anyone have some idea of what to do? Like first off, we're trying to show that if you have some subspace, then the dimension of the subspace plus the dimension of the orthogonal complement is going to equal to the dimension of the whole space there. Right? So what theorem does this remind you of? Does this remind you of any theorem? Does any theorem sort of spring to mind? Haley?
Rank of A plus the nullity
Yeah.
A equals N.
Yeah. So the rank theorem, right? The right. So the right, dimension of the range plus the dimension of the nullity equals n, right? Okay. So so we know by the rank theorem, right? For any a in n by n, that this sort of thing is true. Okay. Okay. So how do we make that relevant? What should we take as our A? We'd like something for which we'd like to use this, right? So let's make an A so that our A is S. Right? What should we use as our A? Let A be something. What kind of matrix would be such that the range of that matrix, that's to say the column space, right? The column space of that matrix would be the same thing as this subspace here.
Invertible?
Any invertible matrix? We have some subspace, and we want to make a matrix so that the column space of that matrix is our subspace. How do we make such a matrix? Well, the column space is the span of the columns, right? The column space is the span of the columns, right? So what should we choose as our columns of A? We want a matrix whose columns, the span of whose columns is S. Right? So what should we choose as the matrix? What should those columns be? Well, vectors whose span is S. In other words, say
Basis.
a basis. Right? So let A be a matrix whose columns are a basis of S. Right? Some basis, let's say x1 to x1. Did you all not know the answer, or were you just sort of shy to say it, or? I shouldn't ask the question. Okay. Okay. Right. In that case, then the range of A is S. Right. Right. By construction, the range of A is S. Right. And what's S perp? S perp is what? Well, that's going to be the range of A perp. Right? Right, so this is going to be an n by R matrix. Right? An n by R matrix. Right? Okay. S perp is our RA perp. Do we know, right, what are we trying to get to? We're trying to say that the dimension of S plus the dimension of S perp, dimension of S perp equals n. Is that true? Well, S perp is RA perp. Do we know anything about RA perp?
Null space of the transpose.
Right? This is going to be the null space of A transpose. Right? Null space of A transpose. Right? So what we have right now is that the dimension of S plus the dimension of S perp is the dimension of RA plus the dimension of the null space of the transpose. Right? Does that get us to N? It should. I mean, you can say yes, it does. We know it's gonna. But why does it get us to N? Why is this the same thing as N? Right? Does the rank theorem help us? We're trying to use the rank theorem. Does the rank theorem help us? Is this the rank theorem?
So will the dimension of null space of A equal to the dimension of null space of A transpose?
No, we don't know that,
Okay.
but we know something similar. The dimension of the range of A, the dimension of the column space of A is the same thing as the dimension of the row space of A, namely the column space of the transpose. Right? We saw earlier that the row space and the column space have the same dimension. Right? So the column space of A and the column space of A transpose have the same dimension. Okay. And now that's good, right? Because A transpose is a R by N matrix, right? R by N matrix. And so when you add these two things together, by the rank theorem, you get N. If we were dealing with A was sort of the wrong size. A was an N by R matrix. Rank theorem wouldn't give us the right thing. Okay. Okay. Everyone all right with that? Any questions? Right. So that's good, right? You're seeing how to put things together, right? You say, well, here's what I'm trying to show, and I know this sort of screams rank theorem, right? This statement sort of says rank theorem all over it. So you keep that in mind, and you think, okay, well, how am I going to use the rank theorem? Well, I need to have. I'm going to try to force this thing into the mold of the rank theorem by creating a matrix for which RA equals S. Well, what matrix has range equal to S? It's going to be one where the columns are a basis for S, right? And so then you go from there, and you get that this is equal to this, which is not quite the rank theorem, but then you remember that we can make this exactly like the rank theorem by recalling this equality of the dimensions. Okay, so you have to have a facility and memory of a lot of facts, but you see how to do it. Right? Okay. Emily, yeah.
Can you use that to then show what he said, where the null space of a matrix is or the dimension of the null space is equal to the dimension of the null space of the transpose?
Is then the dimension of the null space of the transpose equal to the dimension of the null space of the original guy?
Would that only be true if N is equal to R? Because A is an N by R matrix. So if we had, so if we took the dimension of the null space of the transpose, if we had the dimension of the null space, then the range plus the null space would be R, not N, right?
So let me think, right?
Because it is n by r.
So here's the rank theorem, right? A equals, A is an n by n matrix, the dimension of the rank plus the dimension of the null space equals n. Right? We also know that the dimension of the transpose plus the dimension of the null space of the transpose equals m. Right? So these things are equal. So if n is equal to m, that's true. Yeah. So actually, I guess you could have said it at this point because we're dealing.
But
Well,
it's
no,
an
no,
n
no.
by r matrix, not n by n.
Yeah.
So it wouldn't be true.
So if
Yeah, that's right,
R
yeah.
equal to n.
Yeah, if r
Yes.
equal to n, then yeah, that would work. Yeah. Okay. The second part of the theorem. Okay. So we want to see that if you have you have a basis of S and you have a basis of S perp, then the two of them together form a basis of Rn. And it suffices to show that that those guys suffices to show that these guys are linearly independent. Right? Because we have n of them, we know we are in Rn and we have n vectors. Right? So we don't need to show both independence and span. It suffices to show one of them, as you may recall. Okay. So let's show that they're linearly independent. Suppose that you have some linear combination of these guys, and that linear combination equals the zero vector. Okay. Then, if we break it up into the sum from I equals 1 to r, and the sum from I equals r plus 1 to n. Okay. Let's split that thing up into two parts, right? The sum from 1 to n, we break it up into the sum from 1 to r and the sum from r plus 1 to n. Whatever that thing is, let's call it v. So v equals the sum of these things from 1 to r and minus the sum of these guys from r plus 1 to n. Okay. And what do you notice about v? Well, v is in the intersection. V is in S and v is in S perp. Right? Because it's expressed like this and it's also expressed like this. But these spaces are orthogonal to each other, right? And so their intersection is the zero vector. And so that tells you that v is 0. Right? And the end, right? Because then you know that this is equal to 0 by the linear independence of the x1 through xr, c1 through cr must be 0. You also know that this sum is equal to 0, and by the linear independence of the xr plus 1 through xn are a basis, and thus linearly independent. And so all the coefficients, if you get a linear combination equal to 0, all the coefficients must be 0. Right? So this implies that first C1 through CR must all be 0, and also that CR plus 1 through do Cn is all equal to 0. Right? Because these things are, right? Because this is a basis, and this is a basis. Put this into bases. Okay. Right. So these are linearly independent, and so their union is going to be a basis for a space. Okay. Any questions? Simple? Any questions? Okay. Are you all right? Are you okay? Yes. Why is everyone tired? Why is everyone dead today? Are you dead? No. Henry, yes.
Just a quick
Great, thank
question.
you. Thank you. It's like getting a lifesaver. I can hold on to this. Thank you.
Just Titanic changes. You said S
Yeah.
and S perp are both equal to 0. Like
The intersection is 0. The intersection
Oh,
is
the
0.
intersection. Okay.
Right, because they're perpendicular to each other. Anybody who lies both in S and in S perp would be perpendicular to itself. Well, the only vector it is perpendicular to itself is the 0 vector. Right, and so right, what do you see? You see that this vector is a combination of these guys, which means that it's an S, and it's also a linear combination of these guys, which means that it's an S perp. Right? So there's two ways of expressing this guy, right? V is this guy, V is also this guy, right? And you say, oh look, V must lie in S. Oh look, V lies in S perp. Oh, that means that V is 0. Okay, so this thing is 0, and that gives you that the CI's over here are all 0, and the coefficients over here are all 0.
Thank you.
Yeah,
Can
cut
you
please.
explain how you got from first to second step?
From here to here?
Yes.
Okay, all that happens here is you break it up. You say I equals 1 to R of this whatever, plus the sum I equals R plus 1 to N, right? And then you move the second term to the other side and put a minus sign on it. That's all that happens. Yeah, me.
Could you also say, well, could you also say that that V has to be 0 because it's the only thing that equals the negative of itself?
Well, this isn't the negative of itself.
Oh, okay, yeah.
Right. This is from 1 to R, and this is from R plus 1 to N.
Okay.
And these are different. Maybe it's easier to see if I use a different
Yeah.
index here. Right.
Okay.
Okay. Another important notion. The notion of a direct sum. So U and V are subspaces of W, a vector space. If every W in W can be uniquely expressed as a sum of U plus V, where U is in U and V is in V, then we say W is the direct sum of U and V. And we write this as W equals U direct sum V. Okay. So this is the symbol for direct sum. Right? This plus with a circle around it. Okay. For example, if S is a subspace of Rn, then in fact Rn can be realized as the direct sum of S plus S perp. Okay. So right, why is this actually a direct sum? Why? Let, as before, x1 through xr be a basis of S, and xr plus 1 through xn be a basis of S perp. Then from the above, we know that if W is in Rn, then W can be expressed as C1 x1 plus CR xr plus CR plus 1 xr plus 1 plus Cn xn. Right. Right. The union of these bases is going to be a basis for the whole space. And this thing is in U, and this thing is in V. So we know that W can be expressed as a sum. Okay? So the only thing we need to show is that this expression is unique. Is this expression unique? Let's say that suppose W can be expressed as U plus V, and W can be expressed as U prime plus V prime, right? Where U and U prime are in U, and V and V prime are in V. Suppose there are two. Yeah.
Can't we just say that because S x1 to xr and xr plus 1 to xn is a basis for Rn, therefore it's linearly independent from the previous theorem?
That's true, but that doesn't tell you that the expression of is the expression. So it's not that. I think the trouble is some imprecision in the statement here. Is the expression of W as a sum of something in U plus something in V unique? Okay, so it is true that there's only one way to express, this is a basis. So these coefficients are unique. But that doesn't preclude the possibility that with some other basis you might have some other way of splitting it. Right? There might be some other way of expressing W as something in U and something in V. Yeah. But what we'll see here will do it for us. So let's see. So in that case, so suppose there are two ways of expressing it, right? In that case, U plus V equals U prime plus V prime. And that tells you that U minus U prime equals V prime minus V. Right, but this thing on the left lies in U, and this thing on the right lies in V. So as before, we see that whatever this construction is, it lies in U, and it also lies in V. Right, the thing on the left is the same thing as the thing on the right. You can give it some name, right? Xi. Xi lies in U, Xi lies in V, right? And so it lies in the intersection. So Xi lies in the intersection of U and V. Sorry, I've been using U's and V's, but I should be using S's and S perps. S should be S perp. S perp. S perp. S perp. Xi lies in S, the intersection of S with S perp. And so is 0. Right. And so is 0. And being 0, that gives you that U and U prime is equal, U minus U prime is, U is equal to U prime and V is equal to U prime. So U equals U prime and V equals V prime. So the right. So there is no other way to express W as a sum of something in U and a sum of something in V. Still, you all look kind of confused or something. Are you confused? Are people confused? Or close your eyes for a second. Raise a finger if you're confused. Okay, open your eyes, please. Thank you. So most people are not confused. Good. You're just bored. Yeah. Yesterday. Okay, I haven't said this before. Yesterday, I was, to cheer myself up, I looked on the internet for a website of mathematical jokes. Unfortunately, I can't remember any except for some inappropriate ones. So I can't. I have nothing to entertain you with. But yeah, go look for some mathematical jokes. They're kind of funny. Okay. So direct sums, and okay. Well, at this point, you'll be it's sort of confusing. Why do we care about direct sums, right? you have some way of splitting your space into a combination, right? Into a sum of subspaces, right? Into some sort of sum of subspaces. Why is that useful to us? In the next section, that will be made very transparently clear what's good about this. The next section we'll do the method of least squares, which is a very useful tool that whose extension is sort of like it's not inaccurate, I think, to say that the business of big data is an extension of the method of least squares. It's sort of like a super refinement of the method of least squares. Okay. Maybe something to get 2 more facts in, but we only get 1 more. Last fact, as a subspace of Rn, then the orthogonal complement of the orthogonal complement is actually your space again. Okay. Proof. Showing that S is contained in the orthogonal complement of its orthogonal complement is maybe easier. So let's say that B is in S. We know B then is perpendicular to any Y in S perp. Right? So what does it give us? That gives us that B is then in the orthogonal complement of the orthogonal complement. Trivial. The other direction, we want to show that if you're in the orthogonal complement of the orthogonal complement, then you must be in the original space itself. Okay. So let X be in the orthogonal complement of the orthogonal complement, right? In other words, X is orthogonal to any Y in S perp. X is perpendicular to anybody in S perp. So now we know one thing, that we can express S as U plus B, where U is in S and B is in S perp, right? By the previous statement, right? We know that since Rn is S direct sum S perp, that we can express S as a sum of somebody in S and somebody in S perp. Okay. So we're hoping here's the claim that B must be 0. Okay. That second part is going to be 0. That's good. That will mean that X is actually something in S, which is what we're hoping to show. Right? We're hoping to show that if you're in here, then you are in S. Okay. So that's what we need to show. Right? So y. Take the scalar product. Consider X the scalar product of X against V, X against V. Right. Right. So remember, X is in S perp. V is in S perp. Right. So this is going to be 0. Okay. Because one is in the orthogonal complement of the other. Okay. So that is the same thing as VT of U times V. Right. X is U plus V. Right. V is in S perp and U is in S, so this first product vanishes, right? We get VT U, which is 0, plus VT V. Right? V transpose V. Right? And that shows us that V is 0, right? Which is what we're hoping for. Right? That tells us that the magnitude of V squared is 0, which tells us that V is the 0 vector. Right? And so V is the 0 vector, and so X is actually U, which is an S. Yeah,
Why
Mia.
does VTU go to 0?
Well, remember, U is in S, right? U was in S, V was in S perp,
Oh, okay.
right?
Yeah,
So
okay, I see.
they're perpendicular to each other, right? So that's going to be 0.
And then VTV equals V's. Yeah, okay.
Right, that's just the dot product of a vector against itself is the magnitude squared. And so we get 0 equals the magnitude squared of V, and so V is the 0 vector. Okay. Okay, so next time we'll finish up with something that's sort of interesting, a way of understanding more more concretely why the dimension of the row space and the dimension of the column space are equal to each other. We'll see that in fact we have an isomorphism that this thing gives us an isomorphism, which is pretty nice. And then from there we'll do the method of least squares, which is a nice application of linear algebra.